Morning, and thank you for attending. Today's webinar is Mass Flow Controller Troubleshooting, presented by Doug Baker, the Director of Sales and Business Development for Hastings. We will be taking questions throughout the presentation, so feel free to submit those using the question feature. And I will go ahead and turn it over to Doug.
Oh, thank you, Shelley. Hello, and welcome to today's webinar entitled Mass Flow Controller Troubleshooting. This webinar is being recorded and will be posted on our website at teledyne-hi.com. It will also be uploaded to YouTube, and copies of today's slides will be available to all our registrants for download. As Shelley mentioned, we will take questions throughout the presentation, and we'll address those at the end. All right, my name is Doug Baker, Director of Sales here at Teledyne Hastings. And I'm honored to have with me today Mr. Antonio Cristia, who is VP of Engineering at Semiflow Engineering in Sunnyvale, California. Now, to approach the topic of mass flow controller troubleshooting, this webinar will be presented in three broad sections. In the first section, we're going to quickly review the basic elements and operation of a thermal mass flow controller, also known as an MFC. Next, since it's been said that over 80% of MFC issues are caused by improper or poor installation, we're going to review some of the pitfalls that we see when it comes to installation of a new MFC. Then we're going to get into the topic of older installations of MFCs and discuss some of the issues that may creep in and cause your controller's performance to deteriorate. And finally, we're going to tell you about the resources that are available to you when you want additional help on an MFC question or issue. So let's get started. We're going to start by taking an overview of the basic elements of a mass flow controller. And we're going to start with a thermal mass flow sensor and then work our way around moving counterclockwise. Of course, a properly functioning flow sensor is very important. So let's take a closer look. The flow sensor will contain a small diameter capillary tube, some form of heating element, thermal sensors, and supporting electronics. So what we're showing here is the flow sensor without all the supporting electronics. Now, there are several different configurations and techniques for these sensors. Each has their own set of advantages and disadvantages, and we're not going to get into all that today. But the thing to keep in mind is that the capillary tube is core to the flow measurement. It has a small diameter, so if you encounter debris, oil, corrosion, all those fun things that Antonio is going to get into later, the flow measurement and the flow control are going to be compromised. Okay, let's go back to our overview slide. The next thing we're going to talk about is the bypass shunt or laminar flow element. MFCs are designed such that most of the flow passes through the shunt. Only a fraction of the flow actually goes up through the flow sensor. So what I've shown in this image is the location of the sensor taps or ports to the flow sensor. So now as flow travels down the shunt, there's a pressure drop developed across the flow sensor, which in turn forces gas through the sensor's capillary tube. A well-designed shunt features a stable, predictable flow ratio between the bypass shunt and the flow sensor. Ideally, we want to have laminar flow. Everything's well behaved. Now I've shown here a couple of different examples, a smaller shunt shown there on the lower right, and one of our larger shunts shown on the left. Now the bypass shunt is installed into the base, which is usually made from stainless steel. There are system connections or fittings that connect the MFC to the user's piping or tubing. And note, I'm only showing the exit or downstream fitting in this image. So we see the flow travels through the bypass shunt. Remember, some of the flow is going to go up through the flow sensor. Now the flow is heading up into the valve. So let's take a look at the proportional control valve. Now, what do we mean by proportional? Well, a proportional valve can do more than just be either open or close. A proportional control valve can be adjusted to be anywhere in between. Small electrical current is passed through a coil to generate a magnetic field. The field pulls the valve seat off the orifice and allows flow to pass through. Note that the valve is spring-loaded to ensure that the valve is normally closed. In other words, we have to have current in the coil to open the valve. And by extension, if there's loss of power, the valve will be closed. That's what we mean by normally closed. So by adjusting the current in the coil, we control the flow through the MFC. The important takeaway here is that the valve's orifice can be very small. For example, we make orifices that are as small as 1/1000th inch in diameter. Now, the difference between a fully closed valve and a fully open valve is that in the fully open valve, the valve seat will be lifted off, will be positioned by the magnetic field to be about a little bit more than 1/4 of an orifice diameter above the orifice. So we're talking about very small dimensions. So that's really cool that our electronics and mechanical construction can be that precise. But as we talk about contamination and corrosion later, you can already see how a precision valve is going to be challenged. One more note about the orifice. Teledyne supplies an entire range of orifices for a broad range of flow rates. We review the user's flow rate, gas type, upstream and downstream pressure, and then select the optimal orifice. And we'll talk about this more later when we get into installation. Okay, let's put all the elements together and talk about the control loop. In the MFC's control loop, the circuitry, whether it's digital or analog, is constantly comparing the flow signal, which is generated by the flow sensor, to the command signal. Now, the command signal is being sent by the user of the MFC. Based on that comparison, the control loop determines how much current to send to the valve's coil. For everything to work together and control flow, we need to have a command signal from the outside world. Also, we usually want to know what the flow rate is, so we need to be able to communicate that flow signal outside of the MFC. Now, there are all sorts of ways that the MFC can receive the user's command signal and communicate the flow rate back to the user. A simple method is to use 0 to 5 volt analog signal, where 5 volts corresponds to the full scale of the MFC. Here's a quick example. If I have an MFC with a full scale of 5 SLM, that is 5 standard liters per minute, then a 4 volt command signal would tell the flow controller to go to 4 standard liters per minute. You often see 4 to 20 milliamp input output or 4 to 20 milliamp IO in the automation control world, and MFCs are designed to fit right in. There are also several digital formats that are used by MFCs. There's RS-232, 485, DeviceNet, Profibus, Profinet, EtherCAT. All right, now let's get into some of the things that could go wrong with the flow controller. And as I mentioned earlier, we're going to split our troubleshooting into 2 very different paths. All right, why won't my MFC work? Okay, we're going to split into 2 different paths. I'm going to talk about some of the pitfalls with a new installation, and then Antonio is going to discuss what can happen to an older MFC that's been in service for some time. Now, as we discussed just about a minute ago, an MFC has 2 functions. 1, it will measure the flow, and then 2, it will control the flow. So that's simple enough. Let's ask ourselves these 2 questions. Am I getting accurate flow readings? And am I getting stable flow control? So let's start with the accuracy of our flow readings. Well, there's one check that should be easy enough, right? That is the signal we receive when we know we have 0 flow. One procedure for checking 0 is to allow the MFC to warm up and then close the downstream valve and open the upstream valve. Next, we send a full scale 100% command signal to the MFC, and then we close the upstream valve and send a 0% command signal. We then wait a minute and check the 0 reading. Now, at this point, obviously, we should be getting a 0 flow indication. For example, in the analog world, we should see 0 volts or 4 milliamps. So if that's not happening, if we're getting a voltage that's floating around or current that's not stable, we're not getting that 0 volt or 4 milliamp, there's got to be an issue with the wiring. Now, I want to mention there are a couple of common mistakes that may occur with this technique. You might have a leaky valve, either upstream or downstream, or the MFC might have a small leak across the valve that could lead to an erroneous 0. Ideally, you would measure the 0 output at the MFC because some system displays may not swing and indicate negative flow. So let's talk about the wiring issues of the MFC. If the wiring is not right, then we can't expect to get the desired results. We typically don't see as many issues with 0 to 5 volt analog I/O. We see more issues with 4 to 20 milliamp integration. So let's take a closer look at that. We're going to quickly go through the wiring of a 4 to 20 milliamp I/O mass flow controller that is powered by 24 volts using a 9-pin D connector. So what I've shown here inside the dotted line on the left is the flow controller. Now the numbers just to the right, 1 through 9, correspond to the pins of the D connector. Now to power the unit, we're going to need 24 volt DC on pin 7 and the power common connected to pin 4. We will measure the flow signal using the signal output on pin 2. The 420 milliamp signal will pass through the ammeter and then go to the power common. The flow set point in, that is the 420 milliamp command signal, is generated with respect to the commons. The mistake that we sometimes see people make is that they don't tie the signal common and power common together back at the low end of the power supply. Now the wiring for a 15-pin mass flow controller, which we might use a plus or minus 15 volt DC power, is similar. In this configuration, the commons are tied together back at the power supply. Now a little word of caution. Different manufacturers have different pin assignments, so obviously you can't just willy-nilly plug a cable from one type of MFC into another. Once you're wired up correctly and you're getting a good zero signal, when you run gas through your meter or through the controller, you should expect to see the analog signals respond quickly to changing flow. Now, if you find yourself needing to drill down into the wiring issue, we have some tools that can help. One of the simplest, shown on the left, is a breakout connector that will allow you to measure in and reach and measure voltage levels. And we're happy to loan these out to users to help them troubleshoot. We're also willing to loan out our single channel power supplies if you ever need that, the THCD 100. Now on the right, I've shown a picture of the Flow Nomad, which is available from SemiFlow. This device allows the user to analyze analog signals between the MFC and the power supply. And of course, if you want easy, you don't need to deal with analog or digital signals. You might consider our 300 view flow instrument. All you have to do there is plug in a 24 volt connector shown there, and you're up and running. Okay, remember the two things we're after with a new installation is to make sure we have accurate flow readings and that we are getting stable flow control across the entire flow range. Earlier, we said that we select the valve's orifice based on the user's desired conditions, that is the flow rate, the gas type, upstream and downstream pressure. On many MFCs, these conditions will be marked on the side of the base. So pressures, like upstream and downstream pressure, are very important. If a flow controller is sized for a certain upstream pressure and that pressure is not available, then the flow controller may not be able to reach full scale. On the flip side, if the downstream pressure or back pressure is too great, then the valve may give poor performance. One other note about this topic, some users will just buy a generic nitrogen flow controller, which can be fine. They'll use the GCFs, the gas conversion factors, to go from nitrogen to some other gas. Now, if they try to run large molecules like sulfur hexafluoride using the same pressures through an orifice that's been set up, sized for nitrogen, may not work, right? You may not get full flow through. Or at the other extreme, if you're running a small molecule like hydrogen, you may have issues, right? In these cases, you might see that the valve's going to struggle to maintain stable flow. So anytime you have questions about valve sizing, feel free to give us a call. Now, sometimes we find that in a new application, when a user's setting up for the first time, they may not have a full understanding of the pressure conditions, like what the pressure is right at the entrance to the flow controller. We're happy to work with them to give a wide range of pressure conditions for the valve. And often, if they just give us a simple napkin drawing of the system, that will allow us to help with the MFC selection. Now, a couple of other issues we see with new installations. Users must always ensure that they have the correct line size for the expected flow rate. As an extreme example, you're not going to be able to get hundreds of standard liters a minute of flow through a 1/4 inch line. In general, the fittings that are available for a particular flow controller, like you see on our product bulletins, they'll point you in the right direction towards selection of the correct line size. Also mention that proper selection of a regulator is important. An undersized regulator can lead to oscillations in the flow controller because the instrument may be starved for gas. All right, one last word about new installations. You want to make sure that all your system connections are leak tight. An easy way to do this is with Snoop or Soap Bubble, or if you have access to a helium leak detector, you can find very small leaks very quickly. Okay, at this point, I'd like to turn things over to our guest speaker, Antonio Cristia, who's going to tell us about older installations of mass flow controllers.
Good morning, everybody. My name is Antonio. I am responsible for all engineering aspects at SemiFlow Engineering in California. SemiFlow is a service organization, and we have been associated with Teledyne Hastings for the past 8 years in order to support flow and vacuum installations, service, and craft strategies to incorporate Teledyne Hastings flow products in the various industries that we serve. My task this morning on this webinar will be to point out possible types of failures in existing installations, in older installations, just like Doug said, to look at the possible causes for these failures and provide methods to diagnose and prevent the failure of flow controllers. So going forward, I'm trying to move a slide here. For the older installation troubleshooting, the basic questions that we have at hand are, why did my MFC stop controlling? Obviously, in an older installation, we have a system that has performed, that has worked properly before. All of a sudden, something happens and the MFC has stopped controlling. The flow has become unstable. Why did that happen? MFC does not zero anymore, or maybe a zero procedure has been applied to the flow controller and that didn't work well, or the MFC has started to drift zero, so basically the new zero in time has gone to higher values. Is it time to send the MFC out for service? And we'll discuss towards the end of my presentation some recommendation for the service time. How do I know that the flow is still accurate? These are some of the basic troubleshooting questions that we have. Going forward, I would like to point out some of the influencers of MFC performance. So these are few facts that are influencing the performance of the flow controller, obviously in a negative way. Process conditions would be number one. Every time there is a change in gas or in pressures during the life of a flow controller, there's a possibility that the flow controller will not fit that particular application. Debris and contamination, flow path modification, this is critical. So we'll talk about contaminants a little bit later. Fatigue of system components, it's something that will affect the performance of the flow controllers in any gas line. Gas leakage in system or in MFC connections. And finally, electronic drift or component failure at both system level and MFC level will influence the behavior of the flow controller. These are some of the typical failure modes that we see with a flow controller that has worked in a system and starts to exhibit an issue. The output stays at zero, regardless of command, and there's no flow through the MFC. Output is way higher than 100%, so more than full scale is being exhibited on the output, regardless of command, and we have a lot of flow going through the flow controller. Output signal will not go to zero, and output follows set point at higher commands, but not at the very low set point command. Output signal will not reach full scale, but output will follow set point at the low commands. Controller flow is much higher than expected or much lower than expected. And finally, a thing that has troubled us all in the MFC world, controller has become unstable or oscillates. So let's look at some of this influencers of the MFC performance. And we started talking about pressures. Doug has pointed out how important working with the inlet pressure and outlet pressure in new installations is, and how critical the sizing of the flow controller is based on this inlet and outlet pressure. Teledyne does a great job at marking the pressures on the label of every single flow controller that is being produced, and we replicate that on the flow controllers that are being serviced. So inlet pressure and outlet pressure will affect the behavior of the flow controller. An inlet pressure reduction will not allow MFC to reach higher set points and full scale. So the backup pressure doesn't exist there to sustain the amount of flow that is contained in the full scale of the flow controller. An inlet pressure increase might produce a great overshoot for the flow controller and could also turn into a leak across the valve seat if the inlet pressure is majorly increased compared to the calibration pressure. An inlet pressure increase could actually block the valve operation. There's a certain dynamic on the proportional valve that has to do with how much pressure is needed in order to lift, to allow the magnetic field to lift the valve seat from the orifice. If that pressure increases dramatically, the magnetic field might not be able to lift the valve seat off the orifice. So as a result, you're not going to have control. Instability and oscillations are very obvious things that will happen at inlet or outlet pressure variations. With the outlet pressure, we see problems with reduction in outlet pressure. So, for instance, flow controllers that have been calibrated for atmospheric outlet pressure installed in a vacuum situation could experience instability. An outlet pressure increase, which translates into back pressure, usually turns the MFC into a device that will not be able to reach higher set points and full scale, and of course, instability and oscillations in return. We can go forward. Changing the gas after a while, and this is something that we see with a lot of research and development labs and companies where systems and production all of a sudden change gases on that particular line. So a gas or a gas mixture change normally should point into a recalculation of the MFC full scale capacity, making sure that the MFC will be able to control with the new gas as well as with the older gas that was calibrated for. We ideally recommend those MFCs in this situation to be recalibrated for that specific gas or gas mixture that's going to be used in the process. I would like to point out the danger of cross-contamination. And again, this is specific to R&D facilities where a specific system or bench is used to run a set of experiments, and then the same type of flow controllers, the same flow controllers, are being used with a new gas. The danger here comes from running two different types of gases that are not compatible with each other and can generate a chemical reaction if there's traces of the previous gas in the flow controller. As Doug has presented in the early part of this webinar, the mass flow controller is a very intricate device. So the flow path itself, as streamlined as we try to make it, has places that will allow gas to be trapped. So the moment you run a second gas that is not compatible with the first one, there is a possibility of a chemical reaction between the two gases. That usually doesn't end up well. The most important part here is the elastomeric compatibility with the new gas. So if you have in your facilities elastomeric sealed mass flow controllers, you have to always verify the moment you change gas or the gas mixture that the new gas is compatible with the type of elastomer that you have installed in that particular flow controller. Obviously, one of the solutions is to move up to a metal seal flow controller where all the seal areas are made out of stainless steel. So all the seals are actually metal, stainless steel or nickel in some cases. And this is where some of the compatibility with the different gases, it's not an issue anymore. One word of advice for generic MFC users. we call it generic MFC on mass flow controller that has been calibrated for a neutral gas, nitrogen, argon, air, but during process is actually used for a different gas. Again, I'm going to point out the danger of cross-contamination. The fact that now running sulfur hexafluoride through a nitrogen or an air or an argon MFC means that you will have to recalculate the MFC full-scale capacity using a conversion factor, a gas factor, which is available from all manufacturers, from Teledyne Hastings, or from a service house or a service facility like Semiflow Engineering. Also, I want to point out again towards the elastomeric compatibility with a new gas or the gas mixture that is being used through this generic flow controller. Using a conversion factor in certain situations will increase your error levels to at least 5 to 10%. So one example is to use a nitrogen or an air calibrated MFC to control helium or hydrogen. Although conversion factors are available for these gases, due to the chemistry of the gas and their molecular mass, the actual error that you will experience versus using a mass flow controller calibrated for that specific gas, helium or hydrogen, will reach this levels of 5 to 10% error. As Doug has pointed earlier, gases with different density points will affect stability and response in the usage of a generic MFC. And also standard nitrogen or argon calibrations will not fit gases, heavy gases and gases that require very low delivery pressure. So you will see instability in flow and possibly those particular flow controls not being able to reach full scale consistently during process. We're moving forward. The second influencer and maybe the one that we see the most during our service performance is contamination. We like to call contamination the silent killer. This is actually in tune with a Halloween celebration that we're looking forward to have in a week or so. I will just point out a couple of things that we consider as contaminants. Contamination is a hard word, but actually some of the water and water vapors that might be associated with the process could sneak into the process and could affect the flow controller's performance because it will be considered as a contaminant for the flow controller. Liquid mist and oils, usually associated with pumping situation with vacuum chambers, could affect the performance of the flow controller. Solid powders and solids, if you look at the lower picture that we put there on the left side, you have a very extreme catastrophic failure with debris. This is, we're talking about actually shavings of metal and physical objects that are in the flow path and that can actually destroy the flow element and the flow controller itself. On the upper picture, you actually see a lighter contamination. Nonetheless, an oily film like the one pictured there is as bad for the flow controller performance as the solid contamination. And we'll talk a little bit later why that is happening. Poorly controlled liquid-based gases like tungsten hexafluoride or dichlorosilane that have the possibility of liquefying in situations and parameters that are very close to the process will produce heavy contamination inside the flow controller. Also, gases like xylene, there's a pyrophoric, combining with any potential oxygen from the process lines or from the outside air will produce a beautiful snow-like white powder that will cover the inside of the flow path and will literally block the valve, not allowing the flow controller to exercise control anymore. Next slide here talks a little bit about contamination and how physically affects the functionality of the sensor of the flow controller. And on the upper right side, we have a small section on the sensor tube. Also pictured, we have the elements that are intrinsic to the usage of the sensor. We have a heater and actually an upstream and a downstream temperature sensors. And these are the ones associated with a thermal transfer process. So basically the gas flow will take some of the heat that is pumped into the flow by the heater and will affect the temperature on the downstream sensor by increasing it. The difference between the two will be a measurement of the mass flow that is going through the sample tubing of the sensor. Imagine now that this sensor is actually in the Teledyne Hastings type of design, somewhere in the 14 thousandths of an inch in diameter to a maximum of 26 thousandths of an inch in diameter. But there's MFCs out there from different manufacturers that are outfitted with sensors that go in as low as 8 or 9 thousandths of an inch for the diameter of the sensor tube. So we're talking about a very small capillary tube. The sensor contamination automatically will create a shift in flow values. The thermal transfer measurement process changes with the addition of a contaminant coating layer inside the sensor. So what I picture there with blue is actually a coating. What happens is the thicker the coating, the smaller the diameter of the tube actually becomes from the MFC point of view. So one of the things that we see associated with contamination in the sensor tube is a sudden increase in flow. So if your end process, shows indication that the flow of the MFC has increased dramatically, one of the first places that we will look as a service company when we receive the flow controller to be recalibrated or to be diagnosed in our lab is the sensor area. Also, I want to point out at contamination in the form of liquids. Liquid droplets, like the really nice reddish blob that I feature there inside the sensor tube, can actually act as a thermal short circuit between the upstream temperature sensor and the heater, or the heater and the downstream temperature sensor. This is literally the equivalent of electrical short circuit in an appliance. So the MFC will blast the valve open and then will close, and then will open again and will close. The whole process has to do with the fact that now the thermal transfer process that happens in the sensor, instead of being a smooth, clear operation, reaches the high point and the low point, and this will trigger oscillations of the flow controller or total catastrophic malfunctioning of the flow sensor and the flow controller itself. Go next. We are looking at gas leaks as being a feature that has to do with contamination, and that has to do with a lot of systems out there. There's two major components to a gas leak, and we're looking at a quantity of the gas that actually flows out of the containment, that gets out of the flow path. And we can all appreciate the danger of a toxic gas that actually gets out of the containment of the flow line into the outside environment. Also, there's a inflow point of view that has to do with the gas leaks, and we're talking about the outside air, and specifically oxygen and moisture that could penetrate or permeates inside the flow path. Both are associated with very negative effects, and a corrosive or a toxic gas that will leak out of the containment, out of the system, will produce damages outside the system. Also, moisture and oxygen permeating into the flow path will slowly destroy the lines, will build up contamination, all your components, including the flow controller, damaging and taking it out of control, but also influencing the process, the end result of what the system is supposed to do in a negative way. One recommendation that we do always when we talk to our customers, if you have contaminated devices, and I will point you to the left of this slide where you see this incredible quote from Neil Young, "Rust never sleeps." Sometimes we see devices that are being contaminated, removed from the line, and kept somewhere in a warehouse for a long period of time. What happens is corrosion will continue to affect these devices and that will totally destroy them eventually. What we recommend is customers to immediately block the inlet and the outlet of the flow controller, so capping the inlet feeding and the outlet feeding, upstream, downstream feedings of the flow controller. Double seal them if you have that capability. If not, Ziploc bags are doing a great job. Ship it to a service center that can immediately perform decontamination and cleaning of the device, so we can actually stop that rust right in its tracks and bring the MFC back to its original capabilities. This is what we do in service. We're going next. This is where I took a very basic picture of elements that are found in a gas stick on every single system. And I'll point you out from the left to right. We have a point of use filter. We have a point of use regulator, an upstream and a downstream shut-off valves. And in the middle, of course, the flow controller, which is the one that produces or should produce a stable control amount of gas that has been delivered to the system. And here we're going to talk about fatigue of gas system components. What happens in aging systems with aging components? Some of these components will start to be affected by either contamination or malfunctioning. For instance, one of the things with upstream and downstream valves could be a slow failure of the pneumatic system that is supposed to actuate these valves. And this will generate issues that will be immediately sensed by the flow controller. So this is where we're looking at some of the components issues. And on the right graphic, we have recorded the, with light blue, you see the set point delivered to the flow controller that goes straight forward from 0 to 100%. And then the yellow line represents the output of the flow controller that slowly and nicely follows in a curve format, gets into the 100% without any kind of overshoot, and then stays there in a stable manner, delivering the necessary amount of gas, the prescribed amount of gas into the process. Any of the malfunctioning in this group of components, filter clogging, point of use regulator malfunctioning, either one of the valves, upstream or downstream malfunctioning, will affect the way in which the flow control will perform. Next slide we have will show how we could actually determine what happened to the components based on the behavior of the flow controller. So now we're actually using the signals of the flow controller to debug what went wrong in this very simple system. So I marked with a yellow dot the upstream valve and the green dot the downstream valve. If we look on the right graph, we have the old graph from the previous slide where the normal function of the flow controller is actually described. And then if we have a downstream obstruction, so that means that, for instance, the downstream valve has been affected by contamination, for instance, or the pneumatic line that is feeding this particular valve has been compromised and it cannot do a complete opening of the valve when needed. Imagine that this downstream valve is actually replaced by a very small orifice. Now the valve cannot open completely. So we have a limiting factor. We have a downstream obstruction. What's going to happen is the moment we deliver a set point to the flow controller, and I'm pointing you towards the lower left green marked graph, we'll have the flow controller almost achieving full scale, but then very rapidly the flow decreases till it hits the limit of flow that can go through that downstream small orifice that is represented by a malfunctioning downstream valve. So this is, if you see this kind of signal, this will point you towards a downstream issue. Back pressure buildup in the system, a malfunctioning valve, maybe a line that is getting clogged, maybe a downstream filter that needs to be replaced. On the right side with a yellow dot, I have marked a typical behavior of the flow controller that is involved in an upstream obstruction. So now the upstream valve has the same issue. Again, imagine that valve now is being replaced with a very small obstructing orifice. What's going to happen is once the set point is delivered to the flow controller from 0 to 100%, the MFC will try to react, will increase flow, but will never reach 100% because this orifice, this obstruction placed upstream now will not allow that. So the pressure, there's not enough flow to allow the MFC to go to full scale. The flow will immediately drop to the level that is allowed by this obstruction on upstream. So this is if you have the possibility to record signals, to look at the signals of the flow controller, this is where the flow controller itself becomes a tool in debugging some of the, to get the answer to the question, if I have an obstruction problem, a flow problem, is it upstream or downstream of my flow controller? Either one of the situations, if you detect contamination, it's very possible that contamination is inside the flow controller also, so we recommend service at that time. When you go to the next slide, this is where if you actually decide that you have to remove the flow controller from the system, based on all the things that you know about the system, about the flow controller, and some of the things that you've learned maybe in this webinar, there's a couple of things that we want, if you have the time to do, just to make sure that everything is all right. The voltage supply of the flow controller. So we developed this quick checklist. Look at the voltage supply that goes to the flow controller and make sure that's correct. If you have a 24-volt flow controller, verify that your 24-volt power supply in the system, that the channel that feeds the flow controllers is out there. Use a voltmeter and make sure the 24-volt is within spec. If you have a plus and minus 15 style power supply for your flow controllers, verify both the plus and the minus 15. Keep in mind that usually the minus 15 channel is the one that fails. This is the one that actually delivers power to directly to the valve operation of most types of flow controllers. So there is a chance that the plus 15 power channel will be okay, but the minus 15 will be faulty. If you get, for instance, a minus 11 volts on that particular channel, the power is out of spec. So that's one of the things that should point you in the right directions. Grounding, very important. I think Doug has mentioned how important grounding together. The negatives at power supply are in a plus or in a 4 to 20 milliamp current installation, but grounding has to be consistent throughout the system and has to be consistent at the MFC level. That's something that you can very easily check with a breakout kit, like Doug said, available from both Teledyne and SemiFlow for loaner. It's something very easy. You can check with a voltmeter. Set point of the MFC connector has to be the same as the signal coming from the tool. Many times we see differences at the display of the tool will show 100% set point, but actually if you follow the signal all the way down to the MFC connector, you will see that let's say in a voltage situation, 5 volts translates into a 3.2 volts. So obviously there's a problem with the wiring, grounding, or a cable that is malfunctioning there in the system. Output of the MFC in return has to be transmitted correctly to the tool in order for everything to work fine. One very important parameter that can be measured on most flow controllers is the valve voltage. A lot of the flow controllers will have a pin dedicated to valve voltage. This valve voltage is an indicator of how much struggle there is in the valve in order to exercise control. So monitoring this parameter will tell you if changes have happened inside the flow path, or changes have been happening into the process that will force the MFC to struggle more for that set point that you always deem necessary in the process control. So monitoring, we recommended early on for research facilities or production facilities that are using statistical process control, SPC, to use the valve voltage as a monitoring factor, along with set point, output, and output from different sensors in the process. Exercise control, before you remove the MFC, make sure you change the set point from a low set point to a high set point. And if you have the capability to monitor valve voltage, look at the way in which valve voltage follows that change in set point. If you do not see any change in the valve voltage, something is definitely wrong with a mass flow controller. Basically cannot interpret the change in set point. And finally, compare some historical valve voltage values if you have them with the measure values, and this will give you an indication, a possible indication of what is going on wrong in the system. Our next slide refers to one of the questions that we get very often, and that is, what is the service interval for mass flow controllers? We recommend as a good practice a yearly MFC certification. But the service interval, selecting a service interval should be dictated by lots of factors, and I will highlight here, as you can see on the left side of the slide, historical system data, if you're using statistical process control tools, and why not years 2017, artificial intelligence and machine learning. Literally, the secret here is to find in plots and historical data of different sensing elements, a failure pattern. So machine learning has to do with failure pattern. If you are involved in recording the outputs of the sensors that are in your process, and again, please keep in mind that mass flow controllers can be considered a sensor indicating of life and behavior into that particular system. So MFC signals can be incorporated in triggering and calculating failure patterns using complex math mechanisms as machine learning. The normal triggers that you would use in order to decide on your service interval are your maintenance frequency, numbers of refills and replacements of the gas tanks. We consider every single gas tank replacement or refill to be a generator of particles and contaminants. So obviously, the more tank replacements or refills you do, the more danger for contamination it's out there. There's a lot of facilities that are using process gas totalizers, and there's most of the mass flow controller power supplies, including the ones produced and sold by Teledyne Hastings, and even our Flow Nomad has that gas totalizer function. So you can actually create a scenario in which if you run a certain amount of gas to that line, this will trigger a maintenance call, so a service interval. Sometimes a trigger can be a new process requirement and system reconfiguration. So obviously, if you're reconfiguring the system, you're taking time to do some of the upgrades on the tool. This is a good time to send your MFCs out for service or for reconfiguration or for just a simple certification, just to make sure the functionality is there, the flow values are there, the way in which the MFC is clean and can render the right function. New product implementation, new ISO or product certifications, and new level of product or production quality are also triggers. They're very important, and sometimes one of the things that you want to do in the situations is to send your flow controllers out for service. A new customer, always requiring a new level of quality, can be an indication that you need to revise the standards that have to do with the flow controller service and implement a service interval accordingly. I think this is where my part of the presentation ends, and I hope that I've covered the topics that I promised in the beginning, which were the types of failures.
Thank you, Antonio.
No problem. Thank you very much, everybody, and we value the feedback. We hope to hear from all of the participants to this webinar, and I thank you very much for the time I had this morning. Thank you.
Thanks again, Antonio. And now just a couple of slides to close things up before we see if we have any questions. As we mentioned earlier, we are here to help. You can reach any of our application engineers here at Teledyne Hastings by phone or email at hastings_instruments@teledyne.com, or through the Contact Us link on our webpage, which is www.teledyne-hi.com. And Antonio and his team can be reached at semiflow.com or directly by phone at 1-800-796-SEMI. I'd also like to mention that Teledyne does stand behind our products. We offer lifetime technical support. So feel free to give us a call or email if you have any questions about your gas flow or vacuum measurement application. And for our friends located outside of the Americas, we have very strong service centers in Europe with Shell Instruments, China, Shanghai Jiga, and in South Korea with Infrared. And thank you again for listening. And at this point, Shelley, I don't know if we have any questions.